In this section, we'll be looking at cathodic protection in concrete. We'll build a model using 2D, and we should produce results for the current density for hydrogen evolution, ion oxidation, oxygen reduction, and also make a plot of the oxygen concentration over a period of over different values of pore saturation. And also we should be able to make a plot of the electrolyte potential for a different range of pore saturation values. So we should come up with this results, and I hope you should be able to also produce this on your own after following this tutorial. If there are any questions, kindly drop them in the comment section, and I think we can get started. So we start by opening a model wizard where we select our space. So since we'll be working with the 3D, we select 3D. Then we dealing with AC/DC models in this session. So we go to particle tracing and we select the particle field interactions where we add. So we add all these physics interfaces. Then we move to add our steady. So the steady, look at the charged particle tracing. We want to add by directional coupled particle tracing. So it's used to model interactions of particle trajectories with stationary fields. I think I can go ahead and add done. Okay. So this brings us to our interface. So we can input our parameters, but I would first like to load our parameters, which afterward we'll do some few modifications. So I click here to load parameters, where I'll choose electron beam divergence relativity. So I okay, open, then after loading our parameters, as you can see, we have our initial beam radius, domain radius, domain length, beam current magnitude. With the values, as you can see in here. So the beam current magnitude, I want to make some few modifications and change the value to 1. Expression to be 1 micron. Okay. And also the initial beam velocity, I want to change the value to exponent 6. Then okay, then the maximum mesh element, I want to make this 0.5, as you can see in here. So these are some little modifications that I've done to the parameters. Our new the parameters that we load from file, so we can work with. Then this, I would make the relativistic factor simply 1. I'll just make it 1. As you can see in here. So after we are done with this, we can go ahead to our geometry to start building our geometry. So we add a cylinder where we will input the radius to be R0, height will be L. So it's very easy building the geometry like we do in our usual work. It's very simple. So I want to add a workplane to it, to this work. So I go add a workplane, as you can see. Added a workplane to our work. So building the geometry, adding the workplane is very easy. Just simple steps to follow. I want to make this face parallel. Where I'll select this section. Then I go to the plane geometry that I want to add a circle. So I'll put the radius of the circle to be R0 beam 360. And we have this in here. So I'll go ahead to form our union. And as you can see, it's formed our geometry. So we formed our small circle and our cylinder in here. So as you can see, our geometry has been built quite easily. It's very easy to build it. So I think we can go ahead and add our materials. We want to add blank material to section 1. You input the relative permittivity to be 1. That's for the blank material that we've added. Then we go on to add our variables, where we'll manually input our variables. I think that will help. So let me input our variables here. I think this will take some time, but yes. but there are not many, so we'll finish quickly. Max charge 18 0. So in this section, we will manually input our variables that we can all follow. So done with our variables. I think I'll add the description as well so that you can all follow up. What this is the radial distance from beam axis. This is the beam radius. And this is the average z coordinate. This is the ratio of beam radius to waist radius. So these are our variables and their description, units, and expression that we'll be using for our work. Move to our charged particle tracing, which is the first domain selected. Particle properties too has also, we have predefined definitions. So for the particles species in here, we want to change this to an electron, as you can see. So that you can use this equation to solve. We go to the charge particle tracing and we'll add an inlet. Inlet will be at 5. And we want to make some changes at the release current magnitude, where we want to use the I-beam from our parameters. So we've already defined what the I beam is. I beam value in here. So we move back to our inlet where we will be making some changes. For the initial position, we want it to be density. No, make it density, where we will select the number of particles per release to be 1,000. Initial particle velocity, I want to change this section and make it in here. So the Z side is V beam. So we go on to add an electric force. An electric force will be at the cylinder. We specify the force using an electric field, and the electric field should be this. So we can go ahead and probably we can tag all our work so that we can see all the expressions. So we'll delete this electric force 2. We'll work on the electric force 1. Where we'll specify the force using electric field using this section. As you can see, this is our electric force. So I think we can go ahead and look at the time dependency of field, which should be stationary. We want to use the piecewise polynomial. Go to electrostatics and we want to add ground to our work. And for the ground, we'll paste 1, 2, 6, and 7. So that will be our ground. Then we'll mesh using a user controlled mesh. We move to our side and we want to make changes in the element size parameters. So we change the maximum element size to be H max. As you can see, and we'll select it. So this shows how the machine actually looks like after we do our user-controlled meshing system. Then we go ahead to our study, or we go to the bidirectional coupled particle tracing. And we change the output times in here from want to start from 0, and we want to make a step of 1, 8 in here. Then also we want to stop at 21 to the power 8. So this is how our output time should be. This is what our output time should be. Then we look at the iterations. That the termination method is fixed number. We want to make it convergence of global variable. So in here, the global value is 1, which we want to change to QR max. QR max is already defined in our variables. If we go ahead to check, relative tolerance should be 1 to the power -5. Maximum tolerance should be 0.015. Number of iterations should be 8. So after making these changes, we go to our study where we compute our work. This will take some time to compute. Hopefully, it'll be done quickly so we can make some beautiful plots of our results. So we'll look at results will give us the particle trajectories, electric potential of this, and we'll see how it looks like. Okay, so We have our work done. So we go to our particle trajectory to color expression. We want to change the expression in here to QR T. Yeah. In here. Line style, we want it to be a line. We want to plot as you can see. So that gives us lots of it. In here. So it shows the trajectories of the particle. So it moves from 0, goes quickly up to the final section. You can go to the section and you also change the expression depending on the result we want based on this expression, and that will show what will be at the end. So basically that's it. Showing the particle trajectories in it, the electric potential as well, as you can see. So this brings us to the end of our work, and thank you for your attention, and kindly subscribe if you haven't. So you can also put in your request on the kind of videos you want. I'll make sure I'll go through these comments, and based on them, I'll know the kind of videos that you would also like me to also make on this platform. So thank you very much, and see you on the next video. We start by going to our model wizard, where we select our space dimension. So we'll be dealing with the tertiary electroneutrality. We go to electrochemistry, tertiary current distribution. So we select this. That's the supporting electrolyte, and we add. Go on to steady, where we select stationary, which we go on to add. So this brings us to our Comsol interface, where we go to our parameters, which we'll be loading from file. So when we click to load our parameters, we'll be selecting the cathodic protection in concrete parameters. Alternatively, you could check it from your local DEX Comsol 5.5 or 5.4 multiphysics applications, Comsol model, then you find cathodic protection. So you go on to add the parameters. So we've been able to add our parameters to our work from the tuple slope to apply cell potential. Go on to definitions to add functions interpolation. With our first interpolation, we want to add an interpolation from file, which is sigma. So the cathodic protection in concrete sigma is what we want to add. We go ahead to click to add, which loads our interpolation data, as you can see. Then we name our function sigma. The function units defined as m. So then we want to go ahead to plot it. As you can see, gives us the interpolation. The interpolation results as plotted on the graph in here. We want to add a second interpolation. So we'll load from file, which is the cathodic protection component D02. These are the values, as you see. We want to name the function name as D underscore 02. And the function unit should be M2S. Then we go ahead to plot, have a plot of a function. Subsequently, we go ahead to build our geometry. We start with a rectangle. And since we already have our parameters defined, we have W, which is the width of concrete section. S is the concrete thickness. This R underscore bar is the reinforcing bar radius. So these are the parameters or the the expressions for the parameters which we'll be using. So instead of me actually inputting the actual values, I would have to just input the name of the expression. So I'll just input W or S in here, which makes it easier for our work. So our width is W, our height is L, which is the thickness. The base should be at the corner. So we can build selected and get our quickly if we've been able to build a simple rectangle. We'll continue by adding a circle. Circle, we want the radius to be, as you can see, R underscore V bar. and sector should be 360. Position should be S plus R, sorry, R rebar, and Y should be L. And those selected, we have this. Now we want to make this circle cut through this rectangle. So the circle should cut through this rectangle so that we have a hollow semicircle in here. So how can we do this? If we want to make this circle cut this rectangle that we've actually built. Do this by going to Booleans Partitions, where we introduce difference. So this difference will allow us to select R1, which is, so the object to add is the R1. And so this R1 is the full rectangle. And the object we want to subtract from this rectangle is this, the circle one. That is what we want to subtract from it, so that we can have a semicircle shape formed here. So eventually we'll be able to build this. This is our geometry for our work. Geometry of our work that we'll be using. As you can see, we've been able to add our parameters, interpolation, and build our geometry. Now we go on to start modifying or adding certain electrode and electrode reactions to our work. So at the tertiary current distribution, where you know that this section is the whole section, as you can see, one, defined with all the, is going to solve based on this equation, as you can see. Also will solve it based on this equation. The electrolyte too as well. It's also this whole section. However, when we move to the diffusion coefficient, we select, or we change this value to this PS, which should be isotropic. Charge number should be 0. The electrolyte conductivity should be user-defined. Sigma PS and isotropic. That's the electrolyte current conduction, which is this defined in here for us. Our flux go to insulation, go to initial values. Our initial values will define, before we define our initial values, we want to add electrode surface instead, before we define our initial values. So the first electrode surface that we'll add is this, where we go ahead to select, the section for our electrode surface. Look at our dissolving depositing species. You look at, check our film resistance, check our boundary conditions. We also check potential based equilibrium potential as well. That's for the electrode potential. Go to the electrode reaction for the electrode potential, which we want to name as a zinc reaction, zinc oxidation, sorry. This section is a zinc oxidation. So since it's zinc oxidation, we'll be changing the equilibrium potential. We'll define it ourselves and we'll put it as this zinc. That is our electrode equilibrium potential. Our electrode potential kinetics should also be made as thermodynamic equilibrium. And our heat of reaction should be temperature derivative. These are defined. We go on to add another electrode surface too. So the electrode surface too will select this domain. That's 6 and 7 will be our domain. Move on to the external electric potential, which is E side. Perturbation amplitude 0 from 0, no from resistance. We have average of all reactions. So within this electrode surface reaction, there is an electrode reaction. This electrode reaction for the electrode surface 2 will be termed oxygen reduction. The oxygen reduction, number of participating electrons will be 4. Stoichiometric coefficients should be -1. The equilibrium potential should be user defined, where we select O2. The kinetics expression should be cathodic tuffle, where we have C let's go 0 O2. So I plus I0 O2. So we'll define C later on during our work, which will help us, which will later on make this whole expression known. So during the course of our work, we'll actually change this C to a particular section in the initial value. So that this this exchange current density will actually define. For the benefit of, let me just change it for now. Let me just define what C will be. So we move to the initial values. So in the initial values, we make this C1, we want to choose C1. So we want to use C1. Actually, C1 will be C 0 to F. So that is the value for C1. So the same C1 is going to represent this. That's the concentration. And it's defined in here. So in order not to confuse or to make everyone understand it properly, I've actually defined, I've actually rectified the side to make to be C1. I've made the side C1 because at the initial values, our concentration that we're using is C1. We define it as this. That's the concentration of the oxygen over here and here. Our cathodic taffel slope should be A 0.2 and temperature derivative user defined. Good. So we've been able to make all the changes in the oxygen reduction, the electrode reaction in the oxygen, made all the changes, necessary changes that we have to do. I'd like us to add another, we're going to add another electrode reaction to the electrode surface too. We're going to define this electrode reaction as the ion oxidation. Ion oxidation. That's our equation. The number of participating electrons is 1. We move on to the electrode potential, where we, as usual, we make a user defined in order to put our expressions in here. So electrode potential is defined in here. So all these expressions that we are putting all have been defined in our parameters over here. So that's for zinc, iron, hydrogen, everything is in here. So in case you're wondering why I'm putting these things, they're all in our parameters. Our kinetics, we want to use a anodic type of equation. We want to input our exchange current density as this. We want to input our anodic type of slope as this. Temperature derivative of equilibrium potential is user defined. We're able to modify our ion oxidation. And we go ahead to add another electrode reaction, which is the hydrogen evolution. So as usual, we come to our equilibrium potential, where we change this to user defined and we put in this expression for hydrogen. Also, we change the electrode kinetics to cathodic Tafel equation. change this to this, as you can see, and also we change the cathodic Tafel slope as well for hydrogen. All these expressions are defined in our parameters. All these are for our parameters. This is also user defined. So you're able to make all these necessary changes for the hydrogen evolution. So after this, what we can go on to add is we can add a concentration. We add a concentration to our work. Sorry, concentration to our work. Our concentration should be here. Add the species. We choose species C1, which will define as C score O to score reference. That is it for our concentration. Make sure our electrolyte, everything has been defined properly. Our flags, check first part is overridden. Isolation, first and sixth overridden. Initial values as well. We have defined what our concentration is. In our electrode reaction surface, identify the domain. Think oxidation. Define the equilibrium potential where we input the expression, the value for it. Also the electrode kinetics, we made it thermodynamic equilibrium. When we move to the electrode surface 2, we actually selected the domain. Then we put the expression for the external electric potential. For the oxygen reduction, we put the exchange current density, cathodic Tafel slope, expression we're using cathodic Tafel equation. So as this, number of participating, realize that for oxygen, we used 4 for oxygen. Iron as well. It's same, ensuring that all our expressions are been input correctly. So whilst I'm cross-checking, please can you also check yours to ensure that everything is in order. Just have to double check concentration, which we've defined for 1. So once we've been able to double check all our equations and our expressions, we can go ahead to build our mesh. We want to select an extra fine element size, which we'll go ahead to build. So beautifully, we've been able to build this mesh, which is quite easy for anyone to do. We move to our stationary where we want to make some additions to our state. We want to add an auxiliary sweep to our work. So we select the pore saturation. It should be in the range of, let's say, 0.2. Font intervals of 0.5. Sorry. Results stored, steps stored in this, and also okay. So after doing this, I think we can go ahead to compute our work. So being able to compute our work, which took quite a very short time. So we see the electrolyte current density against potential, showing the potential intensity as we move away from this section towards the other side. So we have our some results that will actually check it out. So as you can see in here, we have been able to compute our results for our electrolyte potential and come up with how the electrolyte potential varies across the whole geometry. Also, we could see the electrolyte potential respect to ground, electrode potential versus adjacent reference as well. So let's go ahead to add a 1D plot group, which we want to name as the rebar potential. Adding a 1D plot group, which is, so this 1D plot group, we go ahead to add, call a point graph. Point graph, we're going to select 3, 4, and 5. We want to find the rebar potential. And our expression, we want to put this CCD dot EVSRF. So it gives you the electric potential versus adjacent reference. Our title should be automatic. Let's make some changes in our legends. want to show our legends and want it to be manual. Want front. Want mid. Sorry. Want front. Want middle. Want black. Go ahead to plot, and as you can see, we have our electrode potential versus adjacent reference. As shown. You can go ahead to add another 1D plot group to show the oxygen concentration. Show the oxygen concentration. So we add a point graph for the oxygen concentration. We select 3, 4, 5, and once expression is C, unit is mole per cube. Which gives us the concentration. Move ahead to show legends. It should be manual. Want to set our own legends. Same as well. Want front, middle, and back. Okay, so this has to be, sorry, this has to be mole. So actually, we should, let me double check this section. We go to check our concentration, oxygen, sorry, I think this is C1. Yeah, this C1 because in our oxygen reduction, the initial equation, we define this as C1 for the oxygen, concentration of oxygen. So when we are doing the oxygen concentration of being a point graph, we have to define the expression as C1. So as you can see, as we define it as C1, the plot has been generated over here. Concentration, oxygen concentration for the front, middle, and back section. We go ahead to add another 1D plot group, which we want to name as the oxygen reduction current density. We add a point graph to this. For our oxygen reduction current density, we add a point graph. The point graph will select this areas and we put this expression TCD dot IOC, which is the local current density. And our legends should be manual. We want to show for front, middle, and back. Wow, so we can see our local current density at the oxygen reduction. For front, you can see the current density is high, and at the, sorry, this is for front, current density very low, or at the back, have a higher current density compared to low, compared to the front. We want to also add another 1D plot group. Which is the ion oxidation current density. So for the ion oxidation current density too as well, we go ahead to add point graph. We select this area, section 3, 4, and 5. And for the expression, we put this expression in there. Put this expression. That's for our local current density. Front is the middle. This is our back. Go ahead to plot, and we have a local current density at the ion oxidation section. For the ion oxidation current density, this is the plot of it. The local current density at the front, middle, and back. That's for the ion oxidation current density. And we want to add another 1D plot group, which will be the hydrogen evolution density. So the hydrogen evolution current density the point graph as well. Go ahead to select this area 3, 4, and 5, and put our expression cd.ilo. So meaning that at the hydrogen evolution, the current density that we'll have for the front, middle, and back. This actually what you're seeing, front, middle, and back. So the current density at the front, middle, and back, if you should make a plot of it, you should have something. Let me name the legends before we can go on. For the front, middle, and back. This is how the plot should be. That's for the hydrogen evolution. Local current density at the back. This is the front. This is the back. So we can see difference in the current density for hydrogen evolution, that of the hydrogen ion oxidation. As you can see, that there's also a difference in the local current density for the ion oxidation. You can also see the local current density for the oxygen reduction in these graphs, as we've shown over for the front, middle, and back. And also we've seen the oxygen concentration for the front, middle, and back. So for the front, middle, and back, these are the concentration values shown over here. We've also seen the rebar potential for the front, middle, and back. And also we should remember that we actually looking at it for a range of pore saturation from 0.2 to 0.8. So the pore saturation, so the range of 0.2 to 0.8. So depending on the pore size, the pore saturation, this is the values of the electrode potentials versus the adjacent reference for the front, middle, and back over this range of pore saturation, as you can see. You can go on to, if you want to see that of the, for instance, if you want to see a different parameter, maybe for the rebar radius, maybe for the concrete thickness, depending on the type of parameter we want to actually study, we can do that. All we have to do is just change the parameter, change the range of values, then we'll be able to make a plot of all these, as you've seen over here. So this is the electrolyte potential over a range of these pore saturation, as we've shown over here. And the electrode potential versus the adjacent reference, as we've shown over here. So this brings us to the end of our section, and thank you for following, and I hope you're able to build this model and you're able to understand what we just did. So if there are any questions, kindly drop them in the comment section, and kindly give this video a like as well. And if you haven't subscribed, please do well to subscribe. Thank you for watching. We will be looking at analyzing the aging in a lamp battery model. We'll come up plotting a graph of the relative cell capacity variation with the cell life and make studies on its different cycling and different states of charge. So I think we can get started now. If there are any questions, kindly drop your questions in the comment section and kindly like the video. So let's get started. We start by going to our model wizard, where we select our space dimension. Then we select our physics. We'll be using a lambda battery. So our battery interfaces, then lambda battery, which we will add. Then we move to our steady. Then we select the steady that we'll be dealing with. We'll be dealing with the time dependent. So we select time dependent and we're done. Which brings us to our interface over here. So we can quickly go ahead to load our parameters. So we click on parameters. Then we load our parameters from file. So we'll call this Comsol. Which brings us here. So we'll be dealing with we'll be working with this parameter, this data, battery capacity loss parameters, which we will go ahead to open. It gives us all our variables in here. We go on to our lambda battery. Also see what we have here. We want to change the operation mode to this. We want to change the applied voltage. We also want to change the battery cell capacity. We want to change the SOC as well. Then we are done in here. Go to the cell equilibrium potential. We want to clear, then reload. Our variable. From our file in here, we choose the capacity loss parameters. So we load this data. We change our reference temperature to T. We go to our voltage losses. So our temperature here should be T. We'll make our potential to change to 1C caps. So we go ahead to include concentration or potential. Tau should be so we can go ahead and add our capacity loss. In here should be user defined, then change our temperature to T. We change this to tau underscore loss. And we have to include our aging factors, which will depend on voltage. Change the offsets to sets. Change transfer coefficients to alpha. We want to include the aging history too as well. Want to make this caps G. We'll go back to our parameters to check. So all that we defined in there has been fully expressed and described over here with a description. The variable is the description. We move to our study and we want to name this as the calendar life. Here the parametric sweep. We want to add parameter name, which we'll call the applied voltage, which will vary from 2. Another parameter, which will be the SOC. We move to the time dependent. We want to change the range for the times to make here 10. So A this way. Should be this way. Go to the calendar live. You want to uncheck the default plot and we want to compute this. So there was an error. Okay, so there was an error that was detected. So we quickly identify the error. And we would like to change this to 3.97. Our parameter value list. Then we can go ahead to compute. So that is the only section I changed. I'll change to, we are changing it. Previously it was 3.94, now I'm making it 3.97. We want to compute. So there we have able to compute. The mistake was actually from this section. That was how come we were able to compute our results. So we move to time dependent. We want to change our range as well. So we've already changed our range and we want to, now that we've been able to compute it, now we want to add a 1D plot group. One D plot group to our work. Then go ahead to name this 1D plot group as relative cell capacity. Then our data set will change it to calendar life parametric solutions. We go on to add a global plot, which we want to change the expression to y-axis as LB dot cell this LB. This will go on to describe it as the relative cell capacity. We want to change the axis to maintain as time and rather change the unit to A. It should be time. Legends should be manual. Show should be 25% SOC. Want to make this to make this 50. We make this 100. Go on to plots, then we have our plots. We move to our relative cell capacity. We want to edit our title, none. Go on to change where our legends will be. We want it to be at the lower left. As we've done over here. So we go ahead to our lamp battery. We want to see change the operation mode to as well to see how it will be. We want to make it a charge discharging cycle. We want to change the discharging cycle to LB. V dot I1C. It should be caps. Should be a negative. This minimum voltage should be minimum. We want to include the reset period. So want to change the resting time to rest. We want to change the charging current to C. So these are some of the changes that we are making over here. The lamp battery section. We want to also change the maximum voltage to this definition. There should be curves. We want to also change the resting time. The resting time in here too as well. Want to change it using the same resting time that we're using over here. And we go on to include the capacity loss, make changes. Capacity loss. We want to include current at our capacity loss. We want our cycling capacity to be big H. Go on to add another steady to our work. We will choose a time dependent steady. Close this. We move to our steady 2 and we want to name this as cycle life. We use the same time for the steady one. We use that for study 2. So we copy study 2. Then we just change this to 1. Let's change this part to the 1. Go to the life cycle, then we uncheck the default plots. We'll go ahead to compute. So actually solving. It will take some time, it will take a while, depending on the CPU of your machine. It takes some time though, so we cannot do anything aside. We wait till this is done computing. It will take some time, but it's very important we allow it to compute, to finish computing so that we can continue. This is taking quite a long time. taking quite a while to finish computing. All we can do is wait some time and let us finish computing. I'm sure for some computers it will take quite a long time, longer time than this. Some too will take shorter time, depending on the RAM of the machine.
Tissue files. Just hold on to something. Right there. Somebody help me also. Okay, so let me see. So we go to our global plot where we duplicate in here. In our data set, we select life cycle solution 6, where we change our legends. Change them to 1 steam cycle. Go to the capacity loss. To capacity loss, then relative cell capacity. That gives us our plot. So we're able to see our different charge cycle with the speed of charge as well. So that's the result of our work, the output that we got at the end of this work.
In this section, we'll be looking at the battery impedance for a 1D model. We'll look at how lithium-ion battery interface can be solved in the frequency domain to predict impedance response in the lithium-ion battery. Also, we'll look at least squares optimizations that can be used to automatically find simulation parameters that best fit experimental data. So we'll end up getting some results as shown in this slide. So I think we can get started now. And if there's any question during the course of this video, kindly put your question down in the comment section and I'll do well to attend to them. So please, let's get started. Thank you. So we start by going to our model wizard. We choose, which brings us to select our space dimension. So this will be dealing with 1D. We select 1D. Then we add our physics. We have to select our physics. So normally to choose lithium-ion batteries, you have to select electrochemistry, come to battery interfaces and choose lithium-ion batteries. Then we add, then we move to our steady. So when we move to our steady, here we have to select the steady that we're going to do over here. So for our steady today, we'll be dealing with an AC impedance with initial values. So this brings us to our work interface. As you can see over here. So we'll be loading our parameters from a file. We'll also load our variables from a file as well. So I'll quickly take you guys through how to load the parameters and the variables from our file. So we click on parameters, as you can see over here. Then you select load from file, which brings you to the files where we have the parameters over here. So you select the one battery impedance parameters, as you can see over here, impedance parameters. So we've actually loaded our files over here. And you can see all the variables that we're using from our parameters, their value, description, and all that. So we see the thickness, negative electrode, thickness, positive electrode, thickness, separator, and many other things over here. As you can see, all these parameters or variables will be used for our model today. We go on to definitions as well to add variables where we'll load from file and we'll choose our impedance. We'll choose our impedance variables over here. So that one is impedance. So as you can see over here, our battery impedance variables. And we load all these. So kindly note that Comsol has detected some of these expressions as unknown since we've not defined them we've not yet defined some of these variables, but as we go on, all these unknown variables will be known, will be defined, and they will turn from this color to black color. So I'd like us to quickly start building our geometry. We build it using a 1D, so we can add an interval. We build by adding intervals to it. So we first build our negative side. So this is the length of the negative electrode. And we build selected. And as you can see, we've built our negative electrode, the geometry itself. So move on to add another interval for the second. We specify the coordinates as intervals, as you can see over here. And we define the left end. And we choose the length, which becomes that of the separator. Then we build. So as you can see, done that for the separator. So we continue this way to build the rest of our models. We add another interval. Choose interval length. It plus separator plus positive. We build selected. This should be underscore. So we go ahead to add our materials, where we first choose our electrolyte. So we add this electrolyte. Double click to add. Afterwards, we add our 2 electrodes. Our negative electrode. Then we go on to add our positive electrode. As we've done over here. We close this material library so we can see our model builder clearly. So we've been able to build our geometry, we've been able to add our materials, we've been able to add our parameters, we've been able to add our variables. So we go on to add a domain point probe. Where we define here as our reference electrode, which is RE probe. Go on to define here as so since we've chosen half of the separator, it was actually indicated over here. Open here, and we see our probe point probe expression. So we change the variable name, and we define it this way. So we want to make this small caps. It's a bit better. So if we should go to our variables, we see that all our variables are now defined. You can go ahead now and quickly add, go to non-components, add integration. So we select a boundary to be at the end. For this. We choose, go to lithium-ion battery, right click, then we choose add a porous electrode. So we add our first porous electrode, but we select where it should be. We've selected that it should be at domain 1, which is the negative electrode. Go to electrode properties as well, and the electrode material should be negative, as we've indicated, clearly indicated. Move on down to check the film resistance, and we want it to be surface resistance. So we want to change the value of this film resistance to film resistance for the negative has been defined in the variable. We want to change the electrode volume to this. We want to change this to this. Electrolyte volume fraction as well. We want to check the electrolyte conductivity and make a user-defined. We want to add a correction factor as well. And the diffusion, we want to make it user-defined and also make it same as well. Same as we did for the correction for electrolyte conductivity. Done same for the diffusion. We want to look at the particle intercalation as well. Look at the particle material. We should automatically be, we have to set it for the negative electrode. Initial species concentration set to we set it this way. And we set the particle mean center surface distance as this. We check the porous electrode reaction as well. Check the material, make sure it is the negative. Change the reference exchange current density as well. We add the porous mixed double layer capacitance to our porous electrode. Where we change this double layer capacitance, we input that of the negative electrode. So it's for the double layer capacitance at the electrode, at the negative electrode side. We go on to add the second porous electrode, which will, since we've done that for the negative, we have to do that for the positive. As we need to change the electrode material as well. has to be that for the positive. Do that for the film resistance, which has to be surface. Do that for positive. Change the electrode volume. Electrolyte volume as well. Change electrolyte conductivity should be user defined. And deviation user defined should be same. Go to particle intercalation, choose our material, MCA. Select our initial species. Particle mean radius, mean center surface distance. Have to select that for the positive. Go to the pros electrode reaction as well. Our material start with the positive. We change our kinetics. We change this to this expression. The active specific surface area has to be user defined. So we add a porous matrix double layer capacitance. L positive. Double layer capacitance is also user defined. It's positive. Go on to add a separator. We select the domain for the separator. So our electrolyte volume fraction is epsilon separate has to be user defined. The activity has to be epsilon sep diffusion has to be user defined. Will be same. Yeah. Our initial values is checked. We'll make some changes at the initial values, where we'll change some of the values in this section. So we'll first change the electrolyte potential. Also change the electrolyte salt concentration. And we want to add another initial value, which will override domain 3. So we add initial values, the second one, which will override domain 3. So we take the same value, this has to be a negative at the end. This goes to initial. This goes to want to add electric ground to it. It should be at this first point. want to add an electric potential as well, which will be at the end. Just if you want to define as this. We want to add harmonic perturbation to our electric potential. We'll define here as we want to add additional porous electrode material as well. It should be that for our positive, as we've selected here. The input here. You click on the porous electrode reaction. And you want to disable this part. And afterwards, we want to add a porous double layer capacitance to this effect. We want to change this to 1. We want to set this to a user defined. S OS 1. So just have to make sure all your expressions are named correctly. We go to our mesh where we use a user controlled mesh. For our work, go to the first size. We want to custom it. We want to set here as 1. Want to go to size 1. We want to select just 2 and 3 for this. Want to maximum element size to be 1. Secondly, set the far end, include the far end in the custom set this as 5. Set as 5, set for 27 to see how it will work. So we uncheck this and this. We go to our frequency domain perturbation. We put our range. This way. Okay, so you notice there was an error. That means we typed place wrong at this should be at this end. Should be this. So we can go ahead and compute and we'll be fine. Good to go. So that's actually worked now. We've actually been able to compute our work. Now we move to steady. Then we want to open our solver. Look at this solver. Solution solver. I want to copy the solution. I want to copy the solution. We want to paste. Now that we've copied, we have to, so we are going to paste it. So we first name this one not optimized. And we'll paste this, the one I've copied it, in a different section. We add a table. We want to name this as experimental
impedance table, which we will actually import. It's a CSV file. You can see over here. We have experimental data over here, and we would like to name this as a reference electrode. Group table. We move to group 1. We want to name this as reference electrode RE. We want to add a 1D plots group as well, which will label as the Nyquist plots. Label this as the Nyquist plots. We want to change our data sets to a different one. We want to use the not optimized solution. We want to change the title to none. Let's check Y and X axis, which is very important. Want to use omega this. We want to paste this here, but we'll change this to imaginary. Forgot brackets. So now Nyquist, we want to add a point graph, which we'll select for. You can also actually click here to paste. It's the same. Now expression,
will be imaginary C ground. It's giving us the units automatically. Parameter, we want an expression. We want the real C ground. We should dates. We have our plots here. Coloring. Line is solid. Let's make it 2. Show our legends. Let's input manual. Show. Call this cell impedance. How about that? We will duplicate this as well. The label will be impedance for NCE versus reference. Okay. Over here, we change our expression. We make here E should be reference of NCE. The expression down here should be the same. As we've done over here. No. We have real zero reference NCE, imaginary zero reference NCE. Take this to name our legend. And we have our plots. We go on to make a duplicate of the same work. And we add we want to make this LTO versus reference. So in here, change this to LTO. So for our expression for the Z, we use LTO.
So we use LTO. This has LTO. It's plotted here, as you can see. We move to our Nyquist plots, where we want to add a table graph. Table graph, we select it as experimental, impedance, and this is reference. Our table, we want to select the experimental impedance table. Our x-axis. So this is our experiment impedance table, the one we imported. Our x-axis, column 2, both column should be manual. So this is actually column 2 is always real and column 3 is imaginary. Go to legends, where we want to show our legends. I want to name this as experimental NCU. So it's plotted in our graph, as you can see. Experimental impedance NCU. Legend, we want it to be upper left this way. Want to preserve the aspect ratio. We want to plot as you can see. We want to conduct a parametric sweep. Go to steady one. The parametric sweep. And how about the load from a file? Load from a file. Load from the file here. And we choose the impedance parametric sweep.
to see how the values will be. You need to study to see, to compute and see. We go to parametric solutions 3. We want to make it parametric sweep. We want to put an Nyquist plot. We want to duplicate. We want to change the duplicated one to a Nyquist plot parametric sweep. We look at the impedance this side, and we want to change data sets from here to parametric sweep. We want to change the legends to as well to reference original settings. We want to input these. CDL plus so minus 2. So positive 1. So we have this minus 3. This should be okay, this should be our film -5. Change this to that and to omega m and side omega m this is this. Out plus 4 10 -7. Okay. 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 Right. Go to the point graph and you want to disable this point graph impedance. You want to disable the impedance for that, so we can see our plot. Now we go on to add physics so that we can add some optimization. We add a general optimization to our work. We close this
side. We want to add a global least square objective. So after adding our global least square objective, we want to browse and load our experimental file. So we've added our experimental data. If you have any experimental data, you could actually use it as well. We want to add a parameter column to this, which you want to define as frequency. So that's the parameter column 1, that's the frequency. We want to add a value column. So this value column will give us this expression. Let's go and see. To name this as the real impedance. To name this as E to 6. Move to the value. We want to duplicate this. We want to make this imaginary. This also becomes imaginary. So we have the real and we have the imaginary. We want to add a steady. Which is within lithium-ion battery. We want to choose an AC impedance. So we move to steady 2. We uncheck these two. So under steady 2, we want to add an optimization. We want to use this type for our method, SNOPT for our method. This actually increase the tolerance, reduce the tolerance, and the least square frequency, let's make it from the least square frequency instead. So we've actually made this from the least square. Down, and we want to set our control variables and parameters. We want to set that for the I naught positive exchange current density. Film thickness of the positive. And we will then set the initial value for this. We'll make set as 1, exponent -3. This will be 1 exponent -3. We add, that will be the CDL positive double layer capacitance for the positive. We add another, that will be CDL underscore volume of positive capacitance, volumetric capacitance. Here we set as 0.5. Here we set as 5. 1 exponent 5. I like to expand this properly. So we want to set this upper bound 1 to 6. We want to set this to 1 exponent -6. So 5 exponent -3. 0.1, 1 exponent 5. Let's set here to be 0.9. Let's set here to be 1 exponent 6. So after setting, we move down, then we go to output while solving. While solving, we plot the default to steady to. We want to show default solver. optimization solver. Want to make this the gradient method as numeric. We set intervals 5 exponent -4. 3. This section. Go to our definitions, and we want to add global variable probe. To name this as exchange. And to input this positive. Want to set the output table. Want it to be same as the and it should be on input 1. Want tables, want to add a table. Want to name this table as optimized. Parameters table. Exchange current density output table. Want optimized parameters. We want to duplicate this and name this as the double layer capacitance. We want to duplicate this as well. We want to name this as the film resistance. Let's see. The film want to duplicate this as well. This will be the volumetric double layer capacity plus electronic So next, we want to also duplicate our next plot. This duplicate should be next plot optimized data, so it should be none for now. Should be steady 2. Solver. No, this should actually be for it shouldn't be here, it should be for here. So here should actually maintain. Here should actually maintain. So these changes, the data set should maintain. However, that for the next optimization is what we have to change. So go to the next optimization, then this is when we change this over here, as you can see. Go down, then marker should be set as square. It should be in data points as well. All these will have to go to simulated impedance NCA versus reference. Okay. Experimental. We want our marker to be square. Go to steady optimization. Now output while solving, we want it to be at the next plot optimization. That's where we want our output should be. So we go ahead and compute. Wait while it computes. So simulated low and okay. Okay. So as you can see, our simulated impedance is our experiment. That's our experimental impedance, and we've actually optimized our simulated impedance to actually meet our experimental values. So if you should go to okay. Okay. Move to Webcam, and let's change this to optimized. We've seen our results being plotted. So this is how we do optimization for our Nyquist plots, and this is a Nyquist plot, an optimized Nyquist plot. So thank you for following to this point, and I hope you're able to make this result. Thank you. Okay, so we would like to determine how to check the capacity field in a 1D battery model. So we're going to use a 1D battery model in Comsol multiphysics to predict the capacity in the battery over a period of time and its aging over a period of time. So at the end, we should be able to plot some results showing the capacity cycle with respect to time, how it changes with respect to time, and also the state of charge as well. So we should make a plot of this as well during this study, showing the discharge curve comparison over a period of time, different cycles, and also the cell voltage during discharge for different cycle numbers. And also we should be able to make a plot of the state of charge at the separator and the electrode boundary, different cycles, the first and the last cycle for the different electrodes. And finally, show the plots of how the capacity ages or varies over a period of time. So let's get started. So at the beginning, we move to our new, go to our model wizard, then from our file, we look at our application library. So when we open our application library, it brings us to this place where we choose lithium-ion batteries and we select capacity fade. We select the capacity fade seed and we open. So when you open, it will take you to the interface and you see all everything defined, the variables. As you can see, variables have been defined over here.
So it's actually inbuilt. All these things are inbuilt in the Comsol setup, depending on the model that we are using. Go to lithium-ion battery, electrode, everything. You can see it has already been, the domain has already been selected. Open our particle electrode has actually been defined. Most of the variables have been defined. To the porous electrodes. So this is basically how it is, and if you should check the materials, you see that it's actually added materials to it. The electrolyte, negative and a positive electrode have been added to it. Go to the initial cell charge distribution. You can see everything has been input over here. So we go ahead to add the charge discharge cycling to it. That will be the first work, and we'll select our domain as form. That is all we select for this section. Discharge current, discharging current we set as -I. Minimum voltage we set as E. Maximum voltage will be max. And charging current will be set as this. Then we check this side, which is include constant voltage charging. And we set this side, which is the upper cutoff, as charge. We would like to start, we go to the start mode, and we want to start with the charge first in this section. We move to porous electrode 1, where check to
we want to add our SEI as row SEI. We want to make this here. This way. That's our dissolving depositing species. We set it as SEI and define the density and the molar mass as well. We go ahead to check this add volume change to, we uncheck this part. And also the film resistance, we want to change it to thickness and conductivity so that we can define the reference film thickness, which we define this way. And we also want to change the film thickness. We want to change it to total film thickness this way. Film conductivity, we want to change it to this. Move to the porous electrode reaction one. We check everything. Then we go and we add a porous electrode reaction to the second one for porous electrode. So over here to go to the electrode kinetics. Then we make here user defined. So we can input our I. Let's go on SEI. Cycle. And let's go on number greater than 0. This way. Move to our variables. We check to see if everything is defined. As previously, those which were in yellow are now black. Everything is now black, as you can see. Go back to porous electrode reaction 2. And we check our coefficient over here, which will make it T underscore factor -1. That is the geometric coefficient of V I
theta. We go to our parameters and we check our t factor as time acceleration factor. Actually 250, yeah. So move back to our first electrode 2 so that we can set our SEI to be t underscore factor. Our temperature should be user defined. We go on to definitions to add an integration. Where we select the negative electrode. We move to our steady. And before that, I want to show default solver. We move to our current distribution initialization. We want to check if everything is in line, but first we will actually modify this part and go ahead to disable our pros electrode reaction too. So you could either click here or just disable over here. So now it's disabled. Our pros electrode reaction too. So you go to current distribution, then you go on to disable pros electrode too. Let's open this solver. On our time dependent solver.
Let's add a stop condition. So we want to add a stop condition to this. That cycles and you also want to add changes part to steps before and after. So this section, we want to uncheck this part. Move to our steady. Want to uncheck generate default dot. So before you study, you need to go to, you need to check all the areas to see whether there's no mistake, especially for the pros electrode reaction 1 and 2. So we check that it should be thing that I've done over here. Material should be graphite, equilibrium material, kinetics as well. This way carefully set it. So this was what we made some changes over here. At the equilibrium potential should be user defined, kinetics user defined, so we go ahead and compute. We have our convergence plot. So we have this. So we move on to let's close this. I want to add a 1D plot group. I want to add a 1D plot group to plot some results which we'll name as load cycle. Name this as load cycle with the title. Type will be none. Plot to y-axis. Our load cycle, we want to add global. We want to input this expression I cell. So now variables I cell is already stated. Move to global. We want to duplicate this. We want to filter as well. We want to put a logical expression over here as first cycle filter. It's been stated in here. We move to global 2. And we want to delete this global 2. Just maintain this global 1 and duplicate it as well. I want to check this. I want to change this expression here to E. When we plot, this is how it should look like after plotting. We want to add 1D plot group. Change the expression to discharge. Curve comparison. Our title to none. Y-axis, rename it as cell potential. Want to add a global. I will name this as the first cycle. Input this expression E cell. Direction. Want to change check and make the parameter an expression. So we input our expression as t as this. This will be our expression for our parameter. And we go ahead to filter and we check this as per cycle filter charge filter. So this has to be, let's go. It's just a star over here. Let's cycle filter. It's a filter here. Yeah, and you're able to plot it. Move to the variables. See, first cycle spotted. Go ahead to duplicate this. How about we check the last cycle? And make this description cycle go to 200, 2000. And we go ahead to filter and make this the last. So we plot, we see.
That's cycle 4. So we make here description cycle for 1. Make the comparison a bit better. We plot. This is the first cycle, and this is the cycle for 2000 to 2000. Go ahead to add a 1D plot group. Change this to SEI, layer potential drop at 1C. Change title. Y-axis. And we change the title to this. And go ahead to label the y-axis as potential drop over let's make this potential drop over CI layer. Go ahead to add a point graph. Select what we want to check. We put our expression in here. Change your parameter to an expression. Change the expression over here to cycle number. Change the description to cycle number. Change the legends to at negative electrode current collector. We move ahead. After adding move to add a filter to it. So we label this as PCH dot filter. We'll duplicate this. In this selection, change it to here. We delete this. And here is that of the separator. To show our legends as well. We duplicate this and change this to electrolyte. Y-axis label changes to electrolyte interaction. And go to our points of change this to yes. We change that of when you have two down one plot. We have this. Plot. We have this graph. I want to add another one, the plot group. Which we'll call capacity fade versus time. So capacity versus time. I'll try to be none. Y-axis show the time and days. And show relative opacity. Go ahead to add global. This becomes Q minus top 1 will score differential of 0. Change the parameter to expression where I name this as T pattern. Let's choose E. Description. I want us to choose time as base ratio legends to now. And we want to show this as based on Webcam 18. Go ahead to add a filter to this. Yes. Charge. Filter. Want to duplicate this and to C one dot T underscore D which starts one
change your legends to nominal 1 to charge capacity. So we will duplicate this. This is cycle number. Change this to cycle number. Expression change to cycle number. Send this to the scene. We plot add another one, the plot group. Sorry, local state of charge at separator electrode interface. This manual. Y-axis is SOC. We add a 4-point global. We add a point graph instead. So select put the expression SOC underscore surface SOC LOC. This is right. Make sure everything is right. Parameter expression. We choose to cdc.t underscore switch. We want to show our legends. So need to show this photo. It's probably let me retype this again. Make your so legends show negative electrode to first cycle. Let's add a filter. It will be the first cycle underscore filter. I want to duplicate this point. And graph. I want to select, deselect this and select side 2, 3. This will be positive. We want to duplicate this again. And change the filter to, I want to duplicate and change the filter to last. Sorry. Last. See. I want to duplicate this, point graph 2, and select it's already selected, so select again here. Okay, so we have 4. 1, 2, 3, 4. Already selected already. We move to, want to check how
variables will actually look. So in our battery, we go to how about look at pros electrode reaction. So this shows the local current density. Before that, for this I'll plot for our local state of charge at separator electrode charge cycle. Right, so attention. So basically that's it. Being able to plot our graphs, and this brings us. Hello guys, we'll be looking at how we could use Comsol to create a model where we'll see the effects of multiple intercalating materials in a lithium ion battery. So at the end, we should produce these results, these plots, and see how the effect of these multiple intercalating materials will be. So I think we can get started now. So we start by going to our model wizard, where we choose our space. We're working with the 1D space. So we choose 1D. Then we select our physics. So we want to use lithium ion batteries. So we click on electrochemistry, and we look for battery interfaces where we select lithium ion batteries. Then we move to our study. We'll be dealing with time dependent with initialization. So we add to click our study. Done. It brings us to our interface, as you can see. So we look at our parameters and we want to load our parameters. Go. Programs files, Comsol files. Batteries. So we will be looking at choosing parameters from here. So when you go to your programs files, applications, battery fuel cells, lithium ion battery, to bring it to this section where you have to load your parameters over here. And you can see we have several parameters that we can work with. There are several parameters over here that has been inbuilt in the Comsol setup, as you can see over here. So we will be looking at the battery, the parameters that we're working with is right over here. We're looking at battery multiple materials parameters, as you can see over here, and we load it. So it brings us here. And when you load it, you get all these parameters over here. So this is what we'll be working with right here for work today. You can go ahead to build our geometry. We add an interval, specify the interval, make it interval length, and we input what the length will be. We want to use lneg, lsep, we want to add L positive. Afterwards, we build the selected, and it's been built over here. So afterwards, we can go ahead and add our material. We add from library. We choose our electrolytes first. Then afterwards, we add our electrode that we'll be dealing with. After adding your negative, you have to add your positive electrode too. So we'll add our MO electrode too as well. And we close this material section. So as you can see, we have two positives and one negative. We'll look at the NCA, look at the basic equilibrium, and look at the interpolation. Let's see how it looks. As you can see, and we will also look for that of LMO, look at the basics, look at the interpolation, and we start to see the difference. See, there's a huge difference between that. Go on to add our variables, which will load from our file. Load from our file right here, multiple materials variables. As shown here. So these are the variables that we will be working with in our work for today. So it's very easy to locate where your variables will be if you follow what I'm doing exactly. We go to lithium and want to add a porous electrode to our work, and we select the domain, which is the first domain. We go on to choose, we look at the, before that, let's open our material section, then to close the side. So at the porous electrode, we go down and we define the electrode material. So we look at the electrode material here, and we want it to be, we've chosen here, so we want it to be the negative electrode, because this domain already is indicated as a negative. And we look at the porous matrix. We want to define this, and you see Comsol has detected it as an unknown variable, as you can see over here. But later on, as we move on, it will be defined. Go to the particle interpolation. Very important, we select the material, which is a negative. we go to particle transport properties, where we look at the species concentration transport. We want to change this to the selection in here. Then we look at the particle mean center surface. We should use that of the negative. Look at particle discretization. We want to change the number of elements. We want to make it 20. In this section. You look at the distribution and we want to make it linear, the particle discretization. And we quickly move to the porous electrode reaction. We look at the material, we choose negative. We look at the reference exchange current density. Choose this. Specify this. Go to lithium. I want to add another porous electrode. We select the domain. We select the electrode material, which is the positive NCA. We change this electrode volume fraction as NCA. Change this to X. We go to effective transport parameter. We make this user defined. Correction factor should be this. Positive. And that of diffusion 2 has to be user defined. And the same same as this. So we did copy and paste over here. So we move to the particle intercalation. We choose our material. Select our material to be NCA. Move to our particle mean center surface, which we change to RP positive of CA. We change the species fixed or to Baker. We did change it to Baker, so we change this to this.
and we go to porous electrode. We change the material to NCA. Change the exchange current density. Oh. All should be in small cups. Then NCA in big cups. In small cups, right? Okay. We go on to add an additional porous electrode material. We select the domain. Then the volume fraction too has to be changed. Like this. Add the particle interpolation. And particle transport species as this. Concentration. We want to change this to solid phase concentration. Defined in here. We go to the porous electrode reaction one, then we want to define the material. We define the material. You have to select the material for this. So our material is positive. Also, we have to change this exchange current density to this. And we change the concentration to insertion concentration. Okay, so some input error, just the small caps has to be small caps I. So we go on to add a separator, which will select the domain,
multiphysize this section, and we replace the Boolean fraction set. Then electrolyte conductivity is user defined. As you can see, also copy this, same for the diffusion, has to be user defined. So we place this in here. So we go on to add initial charge distribution, the initial cell charge distribution. We want to make this section, the initial charge, battery cell setting as state of charge. And we input this value as SOC underscore cell. Yeah. And this section is also underscore there. No, this is but we move to the negative electrode selection, and obviously we have to select this section for it, that because that's a negative domain, and also do that for the positive, select the section. So after doing this, we go on to check where our value was in, it's still unknown. It's because of, this should be underscore and it should be correctly named. So now that all our variables are, we go on to add an electric ground. Want to add an electric ground. We select the section. So it's this point that becomes our electric ground. Then we go on to add an electrode current. Add an electrode current to this as well, which we select where to be at the fourth.
go to defaults, and we want to click here and make our temperature T. We set it to T. We go on to mesh. We want, let's make it fine. Let's build. Okay. Let's go on to add an integration. Then we select boundary for this integration. We want it to be so it's 4th. Let's name this integration as, we set the operator name to be a different name over here. How about we name it as end terminal? So we set that section. How about we move to the current, and we go to the time dependent and we change to 0 to 3, 6. We go ahead to show our default solver. And our time dependent solver, how about we change the times to store as this. And we go on to add a stop condition. We add our our expression. So this will be our stop expression. So our output at stop, we want to deselect and check this. And we want to uncheck the default plots.
and we go ahead to compute. Okay. So we've been able to compute this. It has given us some results. We want to add a 1D plot group. Where we want to name this plot group as constant. Discharge. We want to add a point graph to this. Choose to end. We make a selection. If actually can actually paste this and it will actually be the same. I can use this paste selection to paste it. Right, you can just click on it and go to go. We select the expression over here. Go to lithium-ion batteries. This is our expression that we should be using. Electric potential. When we plot it, gives us electric potential versus time graph of it. You can look at the plot settings. To check and change what should be at the y and x axis. On the y-axis should be the voltage. The title, we want it to be this. We want to make some edit the axis. So, as you can see, so you go on to add another plot group. We add a 1D plot group. We want to name this as a surface concentration of positive.
and we'll add a point graph. We will select this and going to choose particle intercalation. Then is the after solid phase we have insertion, and insertion particle concentration surface. Legends, we want to name this as NCN. We want to plot this. So we have our plots here. We want to duplicate this point graph. We want to change the expression over here. We want to select the insertion particle concentration. So we have insertion particle concentration. This is what we'll actually select for our work. So we just double click on it. It gives us this. Or you can just type this expression over here and that will give you the same results. So we have our plots being done. We go on to the surface. Title, we want to name the title as to name the y-axis as surface concentration. To do some editing of the y and x axis. Okay, so we plot this. We've seen some changes. We want to change the position of the legend over here to upper left. and see. So we go on to a steady solution. We want to duplicate our steady solution one. We want to name this as, but we'll change this here to take the component from this first section. Material tool has been changed. Go to our results. We want to add a 1D plot group. We want to make this a particle concentration. Negative. We change the data sets to this. We do our time selection as interpolated. We need to add a range. To start from 0, step 200, stop at 2000. We want to add this to this. We want to add another range to as well. We want to start at 2032. Step will be 2030. Then 2200. Let's add it. No, we make this 2030 instead. We add another range. And this would be so we inserted or added our time range. We want to add a line graph to this. So we select one. Can also click here to select all, and we have to put our expression for this, which will be
Okay. So we want to plot this, and here we have our plot. Let's check the x-axis. Name this as normalized particle dimension. We check this as well. We want this to be the particle concentration. And we want the title to be this. We add another steady. We go ahead to add a steady for this. Then we choose a time dependent with initialization. Steady 2, we want to change here to 0 to 600. We want to add the parametric sweep to this. We'll add the parameter for which we want to check it. So we choose this and we try to vary within these parameters. Go on to steady. We want to show the default solver. We go to over 3. We want to see the time dependent solver where we want to make the output times steps taken by solver. How about after that we add a stop condition. We input the expression. Which will just be the same as, sorry, this expression. So you can copy and paste, but I'll type it again. Stop. 1 dots and that's the expression. Stop expression.
We want to uncheck this, add warning sign. Okay. We want to also uncheck our default plots and begin to compute to get our results. We begin seeing some results. So we have our results. Now we go on to add a 1D plot group. We name this as voltage profiles. Voltage profiles. We'll make it parametric. We add a point graph to this. We take the data set from our parametric solutions. Highlight, select this point. Now expression to will change to the electric potential. Our legends, we want to show manual. $95 volume 51 mix of NCA and LMO. $25/7 mix. That's 55/45 mix. And we have 75/25 mix of NCA and LMO. We have 525/75. Then we go ahead to plot. As you can see, we have our plot of electric potential time showing different volume mix of our electrode materials. When we go here, we want to change the y-axis to change our y-axis here. I want to name this as just the voltage voltage, and we want to title should be manual, because voltage profiles for different mix fractions for NCA and NCA and O. So after that, we want to manually edit the x-axis and y-axis. Bring this to 0. We need to bring this to 3 and bring here to 0.2. We plot. Okay, so now it makes it more better. Then we want to change our legend position to the lower left. You can see over here. So we've been able to see how mixing different positive electrode materials will have on the voltage on the battery during a period of time, and we've been able to plot these voltage profiles for different mixed fractions of NCA and LMO. Also made a surface concentration plots for the NCA and LMO electrode materials. Also, we're able to do some parametric study on how these different mixed fractions will have on the voltage over a period of time in the battery. So I'm glad we're able to produce these plots in this work that we did today. Okay, so thank you for your attention. Welcome to my channel, and today we'll be looking at how to use a lumped battery model to do a time-dependent parameter estimation. We'll make a plot of the model and experimental cell voltage with respect to the OCV. Also, we'll look at the ohmic charge transfer and concentration voltage losses, look at the plots of all these with the experimental and the OCV, look at the predicted OCV, also look at the voltage of the predicted OCV using the parameter values. So during this work or tutorial, if there's any question, kindly drop your question in the comment section. I'll do well to answer every question that you have. Thank you, and please let's follow to the end. Thank you. We begin by opening a new model. We click on our model wizard, then we choose our space dimension, which we'll be working with. So we select 0D. Then we go on to select lumped battery. So we open electrochemistry, battery interfaces, lumped battery. Then we move on to select our steady. We select time dependent steady. So it brings us to our interface here. So you can see. So we go ahead to add our parameters. We'll load our parameters from our file. So we go on to click here to load, which brings us here. Then we select our parameters. So we select this for our parameter. We go on to double click.
Then it adds our parameter, loads our parameters. So we go on to add our variables as well. Which will load from a file. We select this and load. Now we have our parameters. So later we'll define all these variables so that they will turn from this color to black. We want to add table to our results in here. We want to name it as load cycle table. We want to import from here. So it's just after the capacity loss, we use parameter estimation just after this. So this is what we choose. And click on open to load our file. We go on to definitions, then we want to add, before that, we want to add function interpolation to this, which we will name as E and I versus T. Then our data source will be from result table. It will be load cycle. Our function name, we want to change this. And this as well. I want to change the arguments to S and the function argument S. Go to our variables and we realize that all these unknowns have been defined, now turn to black, which is very, very important, because if they are not identified or they are not defined, we'll not be able to compute our work. So we come to, we check this section as well. We check the applied current, which we'll be using. We want to define it. It's this. We want to also define the battery cell capacity.
And also we want to define the initial state of charge. Okay. We go on to check the cell equilibrium potential. We want to clear this table in here. We want to load from file. We want to choose load our data from file in here. So this will be our file that we want to load. We want to change this temperature to T. We move to the voltage losses. Where we check all these sections. We want to include concentration over potential. We move to steady, then we want to make this a steady load. Load curve simulation. We move to our time dependent, then we want to change our range values. In here. We want to use user controlled and set our relative tolerance to very smaller decimal. We go ahead to compute our work. Which gives us our results. We want to set this as our cell voltage. Title. We want to also change the position to our right for our legend. Move to our global one. We want to set this as our modeled cell voltage. Move to our global 3. We want to put an expression, go to our definitions, our variables, and we choose this. We want to make some small edits on the manual axis. Move this to 305. But we change here to 3.35. Why am I below? Change to 4.2 in here. We update. Move here. What's our source stage of charge? Then we add a 1D plot group. That'll work. Then we'll name this as voltage losses and load, which will go ahead to add a global plot, add an expression, now come to our over potentials, where we select this ohmic over potential, double click to add. So we go on to add another expression. We add one more expression, which will be the activation over potential. We add also the concentration over potential. To this. Once we've added these three expressions, we go on to set the parameter to an expression shown as t. We go on to update our plot. We see our various over potentials shown in here. You can see our ohmic over potential, activation and concentration over potential over a period of time. We want to go on and add the global plot. We'll set this expression as the cell current. We choose this. Then we go on to set the parameter. It's time. We want the line to be dotted. We want the color to be black. We want to plot this. So as you can see, it has been updated on our plot in here. You see the cell current in the graph. Go to our voltage. Take the title off. Want to know what the y and x axis. Want the y axis to be our over potential. You set our y axis to be over potential. And we want to add our global 2 to it. As you can see, it's been updated on our plots. You see our over potential work over a period of time. We want to edit our axis. So it has been updated after making some editing on our x and y axis, and how our plot has been beautifully plotted over here. So we go on to our component 1 to add physics, which we want to do a general optimization. We want to add optimization to this. So we've added our optimization, and we want to do some other, include some other optimization to our work. We want to optimize our work. we go on to add our global least squares objective, which we'll be using for optimization. Our data source, we want it to be from the results table. We want our results should be load cycle table. Our time column should be TS. And our model expression for this should be cell. We want to uncheck this. We go to our voltage losses. We want to set our diffusion, our temperature to T. We want to set our ohmic over potential eta. We want to set our exchange current density. We want to set our diffusion as well. Go on to add another steady. Which will be a time-dependent steady. That will be our parameter estimation. We want to uncheck our default plots. We want to add optimization. Set using this optimization. I want it from least square objectives. Come to control variables and parameters, where we want to add about 3. Ohmic inverse diffusion. So we set our scale 0, 1. So we set them as such. We go on to our definitions to add a global variable proof to our work. Our expression will be eta. Which will go on to duplicate this. It will be this. We go on to duplicate it again the third time. Change this to go to our parameter estimation and want to compute. If you find an error, so there was an error because Comsol detected that this variable is undefined. So we actually go to where this variable is located over here. Then we make sure we input it for this is supposed to be, it's a small l and b dot e caps E underscore CL. So kindly note that this is an L, small l. So can go ahead to compute, which will solve our work for us. It takes some time depending on your computer processor. Okay, so good. That's been able to compute our work. We move to our cell voltage section, where we select our data set to be parameter estimation 2. We'll plot as well. So there is some changes in our work. Then we move to voltage losses. Also, we set our data set to steady 2 parameter estimation. And there too, you can see some changes. Go to optimization. We go down to output, power solving. We check the plot section. Then we go ahead to compute. Okay. We patiently wait for it to finish computing. Okay, so we go to our tables and we add a table which we'll name as our full load cycle. We want to import our data from here. We go to full data, look for full data. Okay, so there's our full data. So this is what we select for our work. Go on to global definitions. Add another interpolation, which we'll name as ENIST full. So our data source will be from result table. Table will be full load cycle. We'll go ahead to name our functions, what our functions will be. E cell, exponent, full. Let's go full. It's 2. Units is S in here. Go on to our variables. We want to duplicate where we change one section to full. No, not that. Change this part. We add full. This section to as well. We change. We add full. This section. We go on to add another steady. This will be a time dependent steady, which we'll call full load cycle. Predictions. We want to change the time. From 1 to 600. want to use user controlled native tolerance. We want to reduce it. We want to modify the model. Disable first variable. We disable optimized. We also change the variables settings to user controlled, where we change the steady to parameter estimation time dependent. We don't want to generate default plots. Move to variables too. Steady one, time dependent two as well. We want to also disable both variables too and optimization. We want to disable them. Steady two, so we want to do same. Disable variable 2, but we leave the optimization for this section. So we can go ahead and compute duplicate our cell voltage. We call this the full cycle prediction. That'll be the full cycle prediction. Dataset should be the full load cycle prediction. We want to do some manual changes to the x-axis. 610. I want to change here to, I would like to plot, see how it changes. I want to change the legends to lower left. As you can see here. Go to global 1. And we want to name this as predicted. Any changes. So you're able to see our predicted ones We go on to add global evaluation. Which we'll name this as standard deviation steady 1. We will have to put in an expression for this, which will be small lb dot copy so xp. Go on to add operation should be standard deviation we want new table. It has evaluated it for us. We're going to duplicate this. Name this as steady2. That will be parameter estimation, which we'll use. And we will also evaluate that data set. Go on to duplicate same, which we'll name 3. We want data set to be follow cycle 3, which we'll evaluate in here. So we want to do a time selection. Want to make a range 0, 2, 1, 6, and 1. Let's evaluate. That gives us our results. We've been able to do an evaluation of this work to see within time range of this what this evaluation will be. So this brings us to the end of this work section. And thanks for following till this end. If you have any question, kindly drop your question in the comment section.